Hi, and welcome to our 123rd test and measurement video. Today we'll look at 12 basic waveforms and see how each is unique. To do this, I've connected via BNC cable channel 1 in a Tektronix AFG 3 1000 series arbitrary function generator to channel 1 in a Tektronix MDO 3000 series oscilloscope. The waveforms are generated internally in the AFG and accessed by going from the home page to Basic, then in the touch screen pressing any of the waveforms, of which Sine is the default. As you can see, the acquired waveform can be seen in the AFG below the main part of the screen, in which various parameters can be adjusted. Using the numeric keyboard, you can change them in small increments so that a large number of variations are possible. The default frequency for the sine wave, as you can see, is 1 megahertz. A million cycles per second. The phase angle is 0 degrees, which becomes relevant when a second waveform is displayed in channel 2, shown in split screen format. Amplitude is 1 volt peak to peak. Offset 0 volts default is the amount the waveform is moved relative to the x-axis in the Cartesian coordinates. Units are volts peak to peak, volts RMS or root mean square, and decibels relative to 0 millivolts at the x-axis. An interesting characteristic of the sine wave, which is vastly important in many natural and human-made phenomena, is that the rate of change is greatest at least amplitude and least at greatest amplitude. Thus, the trace shown in the graph is nearly vertical at 0 amplitude and nearly horizontal at peak amplitude. In this respect, it resembles a swinging pendulum, which decelerates as it approaches the high points in its arc and speeds up when gravitational potential is at minimum. The other interesting thing to note about the sine wave is that all its energy is in the fundamental, or the first harmonic as it is known, and there are no higher order harmonics. This can be seen in the frequency domain, which is accessed in the oscilloscope by pressing the math button in the front panel, followed by the soft key associated with FFT, the fast Fourier transform. Here, the fundamental is the tall spike at the edge of the display, and there are no harmonics. Irregular fluctuating trace at the bottom is the frequency domain display, is the noise floor of the instrument, below which no signals can be displayed. Notice that in this mixed domain oscilloscope, time domain and frequency domain displays of the signal at the oscilloscope input are shown in the same screen. Going back to the time domain, the next waveform on the agenda is square wave. This has a high-level amplitude and a low-level amplitude with almost instantaneous transitions. Since the high and low levels are of equal duration, we say that the square wave has a 50% duty cycle. Accordingly, the square wave is used as a clock signal in the analog to digital converter and elsewhere in synchronous signal processing. The extremely fast rise and fall times are essentially high-frequency components, and as such they generate a range of powerful harmonics, as we can see in the frequency domain. Here the fundamental is lower in amplitude because a large portion of the energy is distributed among the many higher order harmonics. Here is the triangle wave. Notice that the rising edge and the falling edge are linear. In the frequency domain, we see fewer harmonics, quickly falling below the noise floor. A ramp wave has more harmonics because it is part square wave and part triangle wave. The pulse wave resembles the square wave, but its duty cycle may be other than 50%. This is what it looks like at 25%. Notice that in the frequency domain, a fraction of the harmonics is missing. This is the noise waveform. In the frequency domain, we see that it has no fundamental and that it stands out above the random energy, which is a broad spectrum phenomenon. Sine x over x is a function that is used in digital to analog conversion. It is a specialized interpolation mode that yields a more realistic analog realization than merely connecting the dots. Exponential rise is a nonlinear waveform with instantaneous fall time. Other waveforms are DC, shown here with zero offset, Gaussian, representing normal distribution, and Lorentz and Haversine, which are alternate distributions. Thanks for watching. New videos are added periodically, so check back frequently.